Describe the system. There is a complex system in this incident, a series of organizational, teamwork, human errors, in addition to technology that failed the system. Safety system failure as well as group dynamic also had a significant impact in this incident. What is the purpose of the system? In order to operate efficiently and smoothly for the system, it needed to provide a safe environment, preventing any type of incident, and connect and coordinating different parts to achieve the project goals. What are the key components of the system? Human is the key component of any system. Technology, training or lack of training, technical component, operational, and group dynamic are some of the key components in the system. What are key interfaces boundaries? Risk boundaries, safety culture, financial, scheduling setbacks are some of the main key interfaces that led to the incident.
Who are the key actors? The first key actor would be the operators who control the rig for drilling. It was drilling in about 5,000 feet of water, which pushed the boundaries of deep water drilling technology. The second key actor would be the dodgy cement manufacturer that made the cement with formulations that failed to stop the oil and gas that leaked through into the pipe to the surface. The third would be the blowout preventer manufacturer that was supposed to design valves that properly stops the flow of oil and gas. Because both the cement and the valves failed, oil and gas traveled up the pipe toward the surface. Another key actor are the crews at the surface who didn't pay attention to unusual happenings. They should be able to spot a flow of oil and gas toward the surface by looking for an expected pressure increase in the well soon enough 50 minutes before the platform exploded. The person in charge of maintaining the gas alarm is also a key actor because the gas alarm was broken and never fixed, which caused it to fail detecting leaking gas. Last but not least, another key actor is the crew in charge of checking the blowout preventer's battery. The safety device failed to sense abnormality because there were no batteries in it. What tools or technology are involved? Are they manual or are they high-tech? In terms of technology involved, first it's the oil rig that does the drilling. Secondly, it's the pump system, which is an electric motor that drives a gearbox and moves a lever. The lever then pushes and pulls a polishing rod that is attached to a sucker rod that is attached to a pump. This system forces the pump up and down and sucks oil up through the well. What has to be done manually is when the crew has to set up the rig and does the drilling operations. Also, after the rig is removed, the crew has to put a pump on the wellhead for oil extraction. What are the main problems of the system? First of all, it's the rig operators' lack of training because they should have known the boundaries of deep water drilling. Another problem is that the crew at the surface didn't pay attention to abnormalities, and if they did, the disaster wouldn't turn out as worse as it is. Another problem is the blowout preventer and the cement manufacturers who used bad formulations to make the safety devices. Last but not least, another problem is the crew in charge of checking the blowout preventer's batteries and condition of the gas alarm. How is the system's performance measured? The system is measured based on how much oil is pumped up and how accurately they meet the deadline given.
The rig was operated by BP under lease from Transocean, while Halliburton was in charge of drilling procedures. The explosion was caused by multiple failures in a complex system. The project deadline, originally set for 90 days, was weeks behind, costing BP millions of dollars. Rushing the project led to a lack of organization when it came to managing risks, uncertainties, and dangers associated with deep water drilling. On the date of the explosion, events are as follows. 5:53 p.m. They prepare to unlatch from drill and close it for the day. They test the pipes to confirm there are no irregularities in pressure. Pressure spikes, then stabilizes. 6:58 p.m. Pressure was reduced and has stabilized. Pressure test has been misinterpreted. 9:10 p.m. About to unlatch when pressure rises unexpectedly. Valves are closed to stop oil flow. A leak is spotted, only blowout preventer malfunction. 9:31 p.m. Well blows out. Methane gas begins to leak onto rig and poses threat of explosion. Blowout preventer has failed, was found to be improperly tested by a federal board. 9:49 p.m. Methane gas reaches engine room, ignites gas. Blazing crude oil explodes. 130 liters per second of oil are spilt onto the ocean. 400,000 liters per hour. 11 lives are lost in explosion. The rig continues to burn for 36 hours, then sinks to the ocean floor. On April 29, 2010, cleanup of the BP oil spill commenced. No skim and collect method was used, but instead a chemical dispersant called Corexit was used. Corexit works by breaking up the oil into tiny beads, making it less visible and increasingly difficult to clean. This resulted in the death of close to 1 million marine life animals.
The series of events that led to the explosion on the Deepwater Horizon began with the rushing of that current drilling project. The original timeline of the project spanned 90 days, and since BP was behind schedule, the drilling was being done at a pace which caused cracks in the formation that was being drilled. This event was a failure from a social ergonomics perspective, in that the pressure for the company to finish the job led to the neglect of safe drilling rates procedures. 23 centralizers were recommended by Halliburton to stabilize pipes, but only 6 were installed by BP, which makes the cement seal considerably weaker on one side of the pipe. In turn, this act of drilling too quickly led to fractures in the formation that was being drilled. When fluids leaking from those cracks were recognized and the pressure tests were performed, the results were misinterpreted and the issue went unrecognized. This event was a failure from a cognitive ergonomics perspective. Had there been a system in place to account for human error, or in this case, the misinterpretation of the pressure test, the issue would have been identified as being critical. When a leak was spotted and the blowout preventer was switched on, it failed. This was a result of an ineffective test of the blowout preventer. The test that was run on the blowout preventer only accounted for the mechanism as a whole and was unable to recognize 2 faulty wire sets and a dead battery caused by them. This was a clear failure from a physical ergonomics perspective. The test that was being used was unable to recognize whether the device could perform its task, which in this case it did not. When the blowout preventer failed, the methane gas leaked and made its way to the engine room where it ignited, causing the combustion of the Deepwater Horizon oil rig.
On April 20, 2010, the Deepwater Horizon oil rig experienced a high-pressure buildup of natural gas which expanded into the drilling riser and then rose into the drilling rig. The drilling riser's concrete core and usage of nitrogen gas to accelerate the curing was too weak to handle the buildup of pressure and thus resulted in a crack of the core. The reason why the pressure was too much for the core was due to the rig's crew drilling deeper than what the drill could handle. This led to the loss of the hydrostatic control over the well, followed by the failure to control the flow from the well, causing the BOP not to work properly. This allowed the natural gas to rise up the riser into the platform of the rig, resulting in the ignition of hydrocarbon gas igniting and exploding. The rig capsized and sank on April 22nd. This resulted in the riser rupturing. As a result of this, the oil from the drill site began to pour into the Gulf. The United States government estimated a total discharge of 4.9 million barrels, equivalent to 210 gallons, pouring into the Gulf. One of the problems seems to be that the concrete core was too weak to withstand the amount of pressure the riser was undergoing. Another problem was the fact that they were operating 43 days behind schedule. On top of this, the crew had changed the regular testing of the BOP from every 14 days to every 35. Evaluate and create recommendations that can help prevent an accident from happening again.
Better fail-safe, or if the rig capsizes, to seal off the drill/pipe, extracting oil to seal up immediately. In the case of the Deepwater Horizon rig, the drill/pipe used to extract the oil was not immediately sealed up once the rig capsized, resulting in oil leaking into the Gulf. Test BOP every 14 days rather than doing what the rig's team did in switching it to every 35 days to save money. The result of the operating contractors on the Deepwater Horizon rig not checking the BOP every 14 days may have indirectly led to the broader problem of the BOP not working properly the day of the incident.
Safety checks for all the rigs to see if they were capable of reaching depths without problem. Some sort of machine or measurement device to measure the amount of pressure at the deep depths at which the Deepwater Horizon was drilling at may have helped to prevent the problem. Too many parties involved on the rig. Transocean, BP, and the Halliburton Company were all parties responsible for the rig and the day-to-day operations. Transocean was leasing the rig, the Deepwater Horizon, to BP for drilling, and BP was contracting the Halliburton Company to drill and pump the oil. This result of this many parties led to all parties passing the blame for the incident afterward. If there was more cohesion on the rig, it may have prevented this miscommunication and would have made solving the issue easier.
Better structural design on the rig, so if there is a breach to structural integrity in the riser, drill, or core, having a buffer between the source of ignition and the engine room, or a room sealing device to prevent an explosion from reaching the engine room would have prevented the spread of the initial explosion. Some sort of detector or a measurement device to pick up trace amounts of methane gas in the riser and drill, notifying the crew on the rig, preventing them from continuing to work and assess the possible problem.
Implementing strict regulations about safety and technology on rigs' day-to-day operation. Better workplace safety systems and procedures could have helped to make workers more aware of certain signs of possible machinery malfunctions and problems. better time management and scheduling so that the workers on the rig are not rushing to meet an impossible deadline.